Every driver learns the same rule. Keep your tires inflated. Low pressure means poor handling, increased wear, and dangerous blowouts. Soviet military engineers took that rule and inverted it. They built a system that deliberately pumps air out of the tires while the truck is moving at full speed across terrain that should be impassable. The tires flatten. The truck doesn't sink. It does the opposite. And the method they used to deliver air through a spinning axle at highway speed was so mechanically improbable that Western engineers refused to believe it worked until they captured the trucks and took them apart. The rule about tire pressure exists for good reason. On a paved road, an underinflated tire overheats, wears unevenly, and can fail catastrophically at speed. But pavement is rigid, soft ground is not. And on soft ground, the physics reverse completely. A fully inflated tire concentrates the vehicle's weight onto a narrow strip of rubber. On mud or marsh, that concentrated pressure punches through the surface and sinks. A deflated tire does the opposite. As pressure drops, the sidewall bulges outward, flattening the contact patch into a wide footprint. The same weight is distributed across a much larger area. Ground pressure drops. The tire floats on the surface the way a snowshoe distributes a person's weight across deep snow. Reducing tire pressure from highway levels to soft ground levels can double or triple the contact patch and cut ground pressure by half. Soviet military engineers understood this by the late 1940s. The problem was not the physics. The problem was making it work on a truck that had to switch between paved roads and swamps without stopping. A convoy in contested territory cannot pull over and manually deflate 12 tires with a hand gauge. That takes 30 minutes. In an ambush zone, that is not a delay, it is a death sentence. The solution was a pneumatic system that let the driver adjust every tire's pressure from inside the cab while the truck moved at full speed. An onboard air compressor, powered by the engine, fed pressurized air into a central control valve on the dashboard. The driver selected a pressure setting. The system routed air to each wheel, inflating or deflating the tires to match the selected mode. Highway, cross-country, mud, sand. Each mode corresponded to a specific pressure range calibrated for that surface. But here is the engineering problem that made every other aspect of the system irrelevant unless it was solved. The air compressor and control valve sit on the chassis. The chassis does not rotate. The tires sit on the wheels. The wheels rotate at hundreds of revolutions per minute. Air had to travel from a stationary frame into a spinning axle and out to the tire without leaking, without disconnecting, and without failing under vibration, heat, and mud contamination for thousands of kilometers. The first Soviet implementation on the BTR, 152 armored personnel carrier, used external air lines. Flexible hoses ran from the chassis to each wheel hub along the outside of the axle tubes. This worked. It also exposed the lines to shrapnel, branches, rocks, and enemy fire. A single severed hose disabled pressure control for that wheel. In combat conditions, external lines were a vulnerability the system could not afford. The ZIL-157, introduced in the mid-1950s, solved this with a design that Western intelligence found difficult to believe until they physically disassembled captured examples. The airlines were routed inside the axle tubes themselves. Pressurized air entered the axle housing through a rotary seal assembly called a slip ring, mounted at the point where the stationary axle housing met the rotating hub. The slip ring allowed continuous airflow across the rotating interface using precisely machined sealing surfaces that maintained pressure while the hub spun at full road speed. From the slip ring, air traveled through a channel, drilled into the axle shaft itself, then through a passage in the hub assembly, and finally through a valve stem into the tire. The entire path from compressor to tire was enclosed, protected from external damage, and mechanically integrated into the drivetrain. No external hoses, no exposed fittings. The air delivery system was invisible from the outside of the vehicle. The seals were the critical failure point. A slip ring at highway speed, exposed to temperatures from -40 to +50 degrees Celsius, contaminated by road grit and water, had to maintain an airtight seal for the life of the vehicle. Soviet engineers used redundant sealing surfaces and isolated the seal from axle lubricant to prevent oil contamination. The system was not elegant. But it was simple enough to rebuild in field conditions with basic tools, which for Soviet doctrine mattered more than refinement. This was the system that Western engineers dismissed as impractical until physical evidence proved otherwise. Air flowing through a spinning axle, controlled from the dashboard, changing the tire's relationship with the ground in under 60 seconds. But the engineering that made it work inside the axle was only half the challenge. The other half was what happened when the system met real terrain. On firm ground at highway pressure, a ZIL-157 tire ran at roughly 2.5 kilograms per square centimeter. The contact patch was narrow, rolling resistance was low. Deflated to soft ground mode, pressure dropped to 0.5 to 0.7 kilograms per square centimeter. The tire visibly flattened. The contact patch expanded to nearly 3 times its highway footprint. Ground pressure fell low enough for the truck to cross marsh and sand that would stop a conventional vehicle in meters. But deflation created its own problems. A soft tire at highway speed generates catastrophic heat in the sidewall. The flexing rubber builds internal temperature faster than it can dissipate, and the tire fails from the inside out. This is why every civilian driver is told to keep tires inflated. Soviet engineers did not ignore this constraint. They built it into the operating doctrine. Soft ground mode had a speed limit, typically 10 to 20 kilometers per hour, depending on configuration. Exceeding that speed on deflated tires would destroy them. The system was not a magic override. It was a managed trade-off between traction and durability, controlled by the driver, enforced by training. The compressor introduced another constraint. Deflating is fast. Open a valve and air escapes in seconds. Reinflation requires the compressor to pump against the volume of every tire simultaneously. On a 6-wheeled ZIL-157, reinflation from soft ground to highway pressure took several minutes at operating speed. During that window, the truck was vulnerable. Too soft for highway speed, not yet firm enough for full braking. Convoy procedures scheduled reinflation at designated points before reaching hard surface roads. The system also served a function unrelated to soft ground. A tire punctured by shrapnel loses pressure gradually. Without intervention, the tire goes flat and the vehicle stops. With the system active, the compressor continuously fed air to all tires. A slow leak was compensated automatically. The driver might not notice the puncture until the compressor's duty cycle increased. For faster leaks, the system maintained enough pressure to limp to cover. This capability alone justified the system's complexity in military procurement. Cold weather testing revealed the system's most surprising advantage. In temperatures below -30 degrees Celsius, unprepared ground freezes into a rigid surface that supports heavy vehicles without difficulty. But the transition zones, where frozen ground gives way to unfrozen marsh beneath a thin crust, are the most dangerous terrain for any wheeled vehicle. The crust supports the first axle. The second axle breaks through. The truck is trapped with its front wheels on solid ground and its rear wheels buried in freezing mud. Deflating all tires simultaneously before entering the transition zone distributed weight across a wide enough footprint to cross without breaking through. Convoys that had lost vehicles to crust failure before the system's deployment reported near-zero losses after full adoption across the fleet. The Americans took notice. The first U.S. production vehicle with a central tire inflation system was the DUKW amphibious truck, introduced in 1942, predating the Soviet system. But the American approach remained limited to specialized vehicles for decades. It was not until the 1980s, after studying captured Soviet equipment and directly observing Warsaw Pact field exercises, that the U.S. military began integrating central tire inflation across its tactical wheeled fleet. The HMMWV, the HEMTT, and the family of medium tactical vehicles all received the system. The operating principle was identical to the Soviet design: air through the axle, pressure from the cab, footprint on demand. The technology did not remain military. Commercial forestry operations in Australia adopted central inflation systems to reduce road damage and improve access on soft logging tracks. Mining operations use it to transition between paved haul roads and unimproved pit surfaces without stopping to adjust pressure manually. Agricultural equipment manufacturers now offer it to reduce soil compaction in planted fields, protecting crop yields by distributing vehicle weight more gently across cultivated ground. In each application, the underlying principle is the same one that Soviet engineers embedded inside the axle tubes of a Cold War military truck. Lower the pressure, widen the footprint, let the tire work with the surface instead of against it. A fully inflated tire is optimized for pavement. A deliberately deflated tire is optimized for the ground beneath it. The system that switches between them in under a minute through a spinning axle from inside the cab was engineered for a convoy that could not afford to stop. That engineering now operates in vehicles across 6 continents. The axles changed, the principle did not.